4.5 billion years ago, the space we occupy was a dark, featureless cloud, a vast, disorganized expanse of dust and gas floating in the vacuum, until a localized collapse ignites a central reaction. Over time, that initial chaos resolved into a highly ordered system. Today, we observe a strictly structured sun, dense rocky moons, and organized asteroid belts following precise, predictable orbital paths. The mechanism responsible for this transition from a featureless cloud to a structured system is known as primary geochemical differentiation. The structured architecture of our solar system represents the predictable endpoint of physical sorting, a traceable thermodynamic sequence that arranged raw matter into its current position. In astrophysics, differentiation is the process of sorting raw planetary materials by density and thermal properties. Two universal physical forces drive this entire sequence: gravity and angular momentum. Angular momentum controls the initial movement, shape, and distribution of the raw material in space. Gravity controls how that material accumulates, compresses, and eventually separates into distinct layers. The specific interaction of these forces determines whether a planet develops the distinct crust, stable atmosphere, and metallic core required to support complex environments. The process begins when the gravitational collapse of the vast solar nebula forces matter inward. As the radius of this collapsing cloud decreases, the conservation of angular momentum dictates a physical response. The entire system has to spin faster. This rapid, accelerating rotation exerts outward centrifugal force, which forces the giant spherical cloud to flatten out into a rotating horizontal plane. Inside this newly formed flattened accretion disk, the conditions become extreme. Billions of tons of raw dust and gas are packed tightly into a single crowded neighborhood. By compressing a diffuse three-dimensional cloud into a dense two-dimensional plane, angular momentum ensures these microscopic particles collide with enough frequency to begin building mass. When these dust grains collide inside the disk, they stick together, eventually forming the first distinct solid bodies, planetesimals. As a planetesimal accumulates mass, its localized gravitational pull strengthens. A stronger gravitational pull draws in surrounding material even faster, creating a continuous positive feedback loop of accretion. This gravity-accelerated growth produces protoplanets, massive planetary embryos that serve as the direct precursors to full-sized planets. However, these massive gravity wells do not sweep up every particle in the disk. A fraction of the debris escapes capture. We observe these remnants today as asteroids and comets. They are the pristine, frozen leftover material from the early solar system. These unaccreted rocks continue to cross paths with fully formed, differentiated bodies, colliding with their surfaces and leaving permanent, visible scars. These objects provide a critical baseline for geologists. Because they failed to accrete, they act as frozen chronological records of the pre-planetary disk. Moving to the absolute center of the accretion disk, the conditions scale up. Here, the sheer mass of accumulated matter creates pressure high enough to trigger thermonuclear ignition. The sun operates as a giant ball of plasma, organized into a strictly defined, layered architecture, driven by internal thermodynamics. Its internal structure is divided into three distinct regions: the superdense core, surrounded by the radiative zone, and finally the convective zone. Deep inside, the intense energy generated in the core transfers outward through the radiative zone as radiation. The plasma here is so dense that it can take a photon over 100,000 years to push through this single layer. Further out, in the convective zone, energy transfer shifts to physical movement. Huge columns of hot plasma rise to the surface, cool, and sink back down in continuous cycles. Even in a state of pure fluid plasma, the extreme variations in internal temperature and pressure demand that the star segregate its architecture into these specific zones. This stratification continues beyond the interior into the outer atmospheric layers, where solar plasma finally meets the vacuum of space. Here we find a severe thermodynamic anomaly. The outermost layer of the solar atmosphere, the corona, spikes to temperatures of 1 to 3 million degrees Celsius, vastly hotter than the layers directly beneath it. During a total eclipse, this superheated corona becomes visible. It is a massive, glowing aura of sparse plasma extending millions of kilometers beyond the star. These extreme atmospheric temperatures fuel the violent surface dynamics we see as solar flares and prominences. Because the corona's intense heat generates the solar wind, the sun's specific stratification directly impacts the physical environment of every body orbiting the system. If we move from the plasma of the central star to a newly accreted rocky protoplanet, using the early moon as our model, we see the same physical logic applied to solid matter. Violent kinetic energy from billions of colliding planetesimals generated massive heat, leaving the early rocky body completely molten, a liquid sphere of rock and metal. While in this liquid state, gravity sorts the chemical elements purely by density. Heavy metals like iron sink directly to the center, while lighter silicates rise to the outer edge. As the body loses heat to space, it cools into 3 distinct layers based on that density sorting. The heavy, dense core at the center, surrounded by the intermediate mantle, and capped by the outermost crust. This cooling process yields the final, rigid surface we observe today. The rocky crusts that characterize terrestrial planets are essentially just the lightest geochemical slag, the buoyant material that floated to the top of a once molten ocean. Evaluating the solar system as a complete mechanical model shows a consistent output: a star stratified by plasma density, rocky bodies stratified by chemical density, and undifferentiated leftovers remaining in between. A strict causal chain created this structure. Angular momentum forced collisions. Those collisions built mass. Mass generated gravity. Gravity trapped heat. And that heat reduced solids to liquids, allowing physical sorting to take over. The physical laws of the universe mandate this stratification across all states of matter, applying equally to solar plasma and planetary rock. Primary geochemical differentiation is the foundational mechanism of the universe. By sorting chaos into distinct layers, it creates the stable crusts, volatile atmospheres, and magnetic cores that ultimately set the stage for life.